Hi, a warm welcome to our process optimization mini video project. Our group members for this group is me, myself, Raghavendran, Woo Kai Heng, and Muhammad Ashraf. As you can see in this overview, we'll be talking about the problem statement, the optimization formulation, the solution and discussion with the sensitivity analysis, and we'll be also talking about the binary programming part. The Malakov Power Plant in Lumut, Malaysia is one of the largest independent power producers in the country, generating electricity primarily through fossil fuels. As the demand for electricity continues to grow while environmental concerns increase, there is a pressing need to optimize power generation to achieve cost efficiency, environmental sustainability, and operational reliability. The data in the paragraph below is extracted into a table in the next slide. As you can see in this table, the fuel type and the associated cost, emission factor, fuel availability and efficiency is listed in this table, as you can see here. The project aims to formulate an optimization model to minimize the overall fuel cost while ensuring that the power plant meets electricity demand, maintains stable operations, and complies with environmental regulations. In the optimization formulation part, there are three main steps. Step 1, define the decision variables. X1 equals the amount of natural gas used in MMBTU per hour, while X2 is diesel, X3 is coal. While step 2 shows that we have to define the objective function, which is to minimize the cost of fuel for power generation. Fx equals 59x1 plus 42x2 plus 24x3. The last step is defining the constraints, where the inequality constraints are associated with the fuel availability, power efficiency, and also emission factors of all three types of fuel, while the non-negativity constraints is x1, x2, x3 are equal and larger than 0. First of all, using Excel solver, we can see the minimum cost calculated using the Excel solver is 92,038 ringgit per hour, while natural gas has to be supplied at 1,082 MMBTU per hour, while diesel has to be supplied at 500 MMBTU per hour, and lastly coal has to be supplied at 300 MMBTU per hour. As you can see, we have used GAM software as an alternative. On your left is the whole coding for the GAM software, and on your right is the results extracted from the GAM software as well. The variable z, which is the objective function, has the same value as we have found in our Excel solver, which is 92,038 ringgit per hour, and the amount of fuel for diesel, coal, and natural gas also matches the values from the Excel solver. That's about it from my part, and I'll pass it on to Woo Kai Heng.
Hi everyone, I'm Kai Heng. Today I will be discussing an important aspect of our optimization model, the sensitivity analysis. In any optimization problem, we often deal with uncertainties and fluctuations in parameters. In our model, the parameters such as fuel prices, power demand, and emission limits. Sensitivity analysis helps us to understand how changes in these parameters impact our solutions and allowing us to make informed and flexible decisions. In this presentation, I will explain how we apply the sensitivity analysis to our power generation optimization model, interpret the results, and explore its significance in ensuring cost-effective and sustainable energy production. And let's get started. Now, let's discuss the objective function of our optimization model. Our goal is to minimize the cost, which is represented by the equation Z equals to 59x1 plus 42x2 plus 24x3, where x1 represents the natural gas, x2 represents the diesel oil, and x3 represents the coal. Each coefficient in the equation represents the cost per unit of the respective fuel types. The solver determines the optimal mix of fuels to meet the power demand at a lower cost. Now, looking at the allowable increase and allowable decrease values in the sensitivity analysis table, this indicates the range within which the objective coefficient can change without affecting the optimal solution. For example, X2 diesel has an allowable increase of 7.56, meaning if its cost increased by up to 7.56 ringgit per unit, the solution will remain the same. Beyond this range, the optimal fuel combination may change. Hence, this sensitivity analysis helps us to understand the cost stability and plan for possible fuel price fluctuations while maintaining an optimized solution. Let's analyze the constraint and their impact on our optimization model. Each constraint represents a limitation in our system, such as power demand, fuel availability, or emission limits. The final value column shows the current usage of each constraint, while the constraint right-hand side indicates the maximum allowable limit. The shadow price tells us how much the objective function, our total cost, would change if we increase the right-hand side of a constraint by 1 unit. For example, constraint 1, which represents the minimum power demand of 850 megawatts, has a shadow price of 118. This means increasing the power demand by 1 unit would increase the total cost by 118 units. On the other hand, constraint 4 and 5 have negative shadow price, meaning increasing their limits would reduce the cost. The allowable increase and allowable decrease columns define how much we can adjust a constraint before the optimal solution changes. For instance, constraint 1 can increase by 359 megawatts or decrease by 541 megawatts before the cost structure shifted. By analyzing these values, we can determine which constraints are the most restrictive and where we have the flexibility in our optimization model.
Hi everyone, I'm Ashraf. Moving on to the binary programming. Binary programming is used in this optimization problem to investigate the ideal solution for minimizing objective function when facing different scenario cases. The cases shown in this section are as follows. The first one is only one type of fuel can be used. The second one is only two types of fuels can be used. And the third one is if natural gas is used, then coal cannot be used. Let's take a look at the first case, where only one type of fuel can be used. For the decision variable, the positive variable remains the same as the linear programming, but binary variable was introduced in this section where the first y1 is choose natural gas, y2 is choose diesel, and y3 is choose coal. The objective function remains the same as the linear programming. The constraint also remains the same, but we introduce a new constraint where the equation 7 says that y1 plus y2 plus y3 equals to 1. This is the binary constraint. Therefore, if y1 equals to 1, y2 and y3 will have to be 0, so that the right hand side of the equation remains 1. For the second case, where only two types of fuels can be used, the decision variable and the objective function remain the same as the previous case. The constraint also remain the same except equation 7, where we change the equation where y1 plus y2 plus y3 equals to 2 instead of 1. Therefore, for example, if y1 equals to 1 and y2 equals to 1, then y3 must have to be 0, so that the right hand side of the equation remains 2. In other example, if y2 and y3 equals to 1, then y1 has to be 0, so that the right hand side equals to 2. So this constraint fulfills the requirement for the case 2. For the third case, where if natural gas is used, coal cannot be used, the decision variable and the objective function remain the same as the previous case. The constraint also remain the same, but we introduce a new equation into the constraint, where equation A says that y1 plus y3 equals to 1. Therefore, if y1 equals to 1, then y3 has to be 0, so that the right hand side of the equation remains 1. This fulfills the requirement of the case 3, where if natural gas is used, coal cannot be used. For discussion part, for the first case, where only one type of fuel can be used, the minimum objective function Z obtained was 100,300. where in this case only natural gas was chosen as the variable, where the other variable was remained as 0. The amount of natural gas used in this solution is 1700. For the second case, where only two types of fuels can be used, the minimum objective function Z obtained was 95,818, where in this case, x1 and x2 were chosen as the variables, where the amount of natural gas x1 equals to 1502 and the amount of coal used was 300. The amount of diesel remains 0. For the third case, if natural gas is used, coal cannot be used, the minimum objective function Z obtained was 96,520, where the fuels selected were natural gas and the diesel. The amount of natural gas used was 1,280 and the amount of diesel used was 500. For the conclusion part, all value obtained for Z throughout the various types of programming was shown in the table. We can see that the linear programming delivers lowest minimum Z possible due to having this constraint. Case 2 from the binary programming offers lowest minimum Z possible out of 3 binary cases due to its loose binary constraint. And lastly, case 1 has the largest minimum Z possible due to its tight constraint of needing only one type of fuel present in the equation. That's all from us. Thank you.